So now let's look at some other examples that deal with L'Hopital's rule where it's used for the other indeterminate forms. For our first example, let's check out the limit as x approaches infinity of x log x minus 1 over x plus 1. Now the first step to any limits is you plug in this value that x approaches to see what you're working with. When you plug x into the expression, it gives you infinity from x. And here, as x goes to infinity, we look at what happens to the expression. The negative 1 and the plus 1 cease to matter because they become insignificant compared to the highest power terms. And x over x turns into 1. So as x goes to infinity, this expression approaches 1. And so our limit is going towards infinity times log 1, which is 0. Now infinity times 0 is indeterminate, which again means that we don't know what the answer is from that expression. But we also can't use L'Hopital's rule on this. We need one of two forms for L'Hopital's rule. We need either 0 over 0 or infinity over infinity. So before we do any calculus, we have to first do the algebra to turn this expression into one of those. And the way to do it is to use the fact that infinity equals 1 over 0. And so we can essentially rewrite that infinity as 1 over 0. And how that's going to look is the limit as x approaches infinity. This x, instead of multiplying by x, we are going to divide by 1 over x. Because of course, algebraically they're equivalent. When you divide by a term, you multiply by its reciprocal. So divide by 1 over x is multiplying by x. But what this gives us is now we have 0 on top over 0 on bottom. So we can utilize L'Hopital's rule. So I do my notation to show what I'm doing. The derivative of the top is a bit of a handful, so I'll just kind of skip the algebra. It gives you 2 over x squared minus 1. If you would like, you can do the work out yourself. It helps to split them up into two pieces, differentiate, and then combine the two fractions afterwards. And 1 over x differentiates to negative 1 over x squared. Now, if we plugged in infinity at this step, it would still give us 0 over 0. But there is algebra to be done here. So we do some algebra to it. When you divide by negative 1 over x squared, you multiply by the reciprocal. So we get this expression right here. And this still gives us an indeterminate form. It gives us infinity over infinity. But we know how to deal with polynomials. We know that as x goes to infinity, the negative 1 stops mattering. And this expression just turns into negative 2x squared over x squared, which equals negative 2. If you wanted to, you could do L'Hopital's rule a few more times, and it gives you the same answer. So this was an example of infinity times 0. That was the infinity times 0 example. Whoops, times 0. And you do the same process each time. You pick one of those two terms, the infinity term and the 0 term, and you essentially divide by the reciprocal. For another example, let's check out the limits as x approaches 0 of 1 over x minus 1 over sine x. Now let's approach 0 from the right side. Now, in this case, when we plug in 0 from the right side, we get infinity minus infinity, which also is indeterminate, but also is not one of the forms which we can use L'Hopital's rule. So we have to do some algebra first. We have fractions, and so what we do is we combine the fractions into a single term. When we plug 0 into this from the right side, it gives us 0 over 0. So we're in good shape here. And this is how you would treat any limit that gives you an infinity minus infinity. They pretty much always involve fractions, so you subtract the fractions, combine like terms, and use that for your limit. Now we can utilize L'Hopital's rule, so we do. Derivative of the top gives us cosine x minus 1. Derivative of the bottom gives us sine x plus x cosine x. When you plug 0 into this, we still get 0 on top, and on bottom we also get 0, but that's okay. We just do L'Hopital's rule again. The numerator gives us negative sine x. The denominator gives us cosine x plus cosine x minus x sine x. When we plug 0 into this, it gives us 0 over 1 plus 1 minus 0, which is 0. So our answer is 0. Oops, left the screen. So for infinity minus infinity, you would subtract your fractions into a single term and use that for your math. Next example. Let's check out the limits as x approaches 0 from the right side of x to the tangent x. When we plug 0 into this, it gives us 0 to the 0th power, which again is indeterminate, and which again you cannot use L'Hopital's rule on. Now, if there are exponents involved, you have to do a bit more work. Essentially what you do is you let the limits answer equal a. Right, so we turn our question, find the limit, into an equation. The benefit of doing that is that then you can do algebraic operations to both sides of the equation. In this case, we have an exponent that is making our life hard, so logarithms are the natural choice, because logarithms allow you to simplify complex expressions. Now on day 1, for our first live lecture, we learned the substitution property of limits, which lets us do this step right here. We can take this log and put it inside of our expression. If this seems a bit confusing, just go back to that day 1 lecture, look at the handout I gave you for properties of limits, and one of the last ones on there, the substitution law, says something along the lines of this. If you have the limit of f of g of x, it's the same as f of the limit of g of x. We're just doing that in reverse here. We have the log of a limit, so that is the same as the limit of log of the function. And why that is useful to us is we can now bring that tangent x down in front of our logarithm. When we plug 0 into this, tangent of 0 is 0. Log of 0 from the right side approaches negative infinity, so we have 0 times infinity, the little tiny infinity. So we have to rewrite this before we can use L'Hopital's rule. So I'm going to make it log x over cotangent x, because now this gives us negative infinity. Cotangent x, as x approaches 0 from the right side, is giving you positive infinity. Right, because cotangent is cosine over sine, and as x goes to 0 from the right side, sine's approaching 0, so the whole expression is going towards infinity. So this is L'Hopital's rule territory. So we do L'Hopital's rule. Derivative of the top over the derivative of the bottom. Cotangent differentiates to negative cosecant squared. Clean that up a little bit. This is the limit as x approaches 0 from the right side of negative cosecant squared. When you divide by that, that is multiplying by negative sine squared over x. We get 0 over 0, so we use L'Hopital's rule again. Hopefully the question's almost done because I'm short on space. Negative sine squared x differentiates to negative 2 sine x cosine x. x differentiates to 1. And when you plug 0 into that expression, it gives you 0. Which is not the answer, because the start of this whole chain of equal signs was log a. So log a equals 0, where a is the answer. That means that a is e to the 0th, a is 1. So when you treat an indeterminate form with an exponent, what I find to be the best way is to let a equal the answer, take the natural log of both sides, use the property of limits to put the log in the limits, and then use the property of logs to put the exponent down. Then you do all your work. Once you have an answer, then you force yourself to remember that you started off this chain of equal signs with log a. So log a is 0, therefore a is 1. A being the answer. Let's do another one. Let's check out the limit as x approaches 0 from the right side of cosine x to the 1 over x squared. So first we plug in 0, see what we're working with here. When we do that, it gives us 1 to the infinity, which is indeterminate. And so we have to first change the structure of the algebraic expression into either 0 over 0 or infinity over infinity. And it's kind of the same thing we did last time. Whenever the exponent is the problem, you let a equal the answer to your limits. Oops. You take the log of both sides. The properties of limits allow you to put that log into the limits. And the property of logs lets you put that exponent down to the front. And then before we do the rule or even try to find the limit, we'll just rewrite that expression a bit. We'll just put it over x squared. So instead of 1 over x squared times it, just divide by x squared. You plug 0 into that. Log of cosine 0 is log of 1, 0 over 0. And we can use L'Hopital's rule. The derivative of the numerator is negative sine over cosine, which is negative tangent. X squared goes to 2x. This still gives us 0 over 0. No big deal. We do it again. Negative tan x differentiates to negative secant squared x. 2x differentiates to 2. When you plug 0 into this, it gives you negative 1 over 2. Which means log a is negative half, which means a is e to the negative half, which is 1 over the square root of e. Both those forms are just fine for an answer, but there you have it. And so it's kind of strange, because this means that in this case, 1 to the infinite power gave you 1 over root e, which I think is definitely a surprise result. Moving on to the one more example. And don't forget, everybody, that if I'm going a bit too fast through the examples, it's taped, right? So you can pause and go back and check everything out. As our last example, the limit as x approaches pi over 2 from the right side of tangent x raised to the x minus pi over 2 power. You plug pi over 2 into this. Tangent of pi over 2 from the right is positive infinity. Pi over 2 minus pi over 2 is 0. Indeterminate. There's an exponent involved, so we let a equal the answer. And then we log both sides. And don't forget that when you take the log of a limit, you can put the log into the function, which allows us to use the property logs and bring the exponent down to the front. This gives us 0 times infinity, so we have to do one more step before we can use L'Hopital's rule, where we divide by 1 over x minus pi over 2. Algebraically equivalent to the expression above, but now when we plug in pi over 2, it gives us infinity over infinity. Both positive infinities. So we use L'Hopital's rule. Tangent x differentiates to secant squared. 1 over x minus pi over 2 differentiates to 1 over x minus pi over 2 squared. We could, if we were so inclined, plug pi over 2 into this, but it's actually better to do some math to rewrite this. Oops, I actually made a pretty big mistake in there. I was wondering where the log went. I forgot it. This log should be right here. This log should also be right here. And secant squared x, log tan x differentiates to the derivative of the inside over the inside. This is the kind of thing that, were we in class, somebody would have pointed this out to me, like back up here, before I went like 5 steps in the wrong direction. But now we're on firm ground. We simplify this. When you simplify this, it gives you negative x minus pi over 2 squared over cosine x sine x. How that happened is you divide by this fraction, which means we can multiply by its reciprocal, and then secant squared tangent is 1 over cosine squared times the reciprocal of tangent, 1 over cosine squared times cosine over sine, and that gives you right there. We plug pi over 2 into that. It still gives us 0 over 0. So we do L'Hopital's rule again. The numerator, when we differentiate, gives us negative 2x minus pi over 2. The denominator gives us cosine squared minus sine squared. And now we're finally in good shape. When we plug in pi over 2 to that, it gives us 0 over negative 1, which is 0. And so log A equals 0. The answer is e to the 0th 1. Okay, so that was one example of each of the other 5 indeterminate forms. And whenever you encounter one of these, the algebra to turn it into 0 over 0 or infinity over infinity is pretty much what I just did there.